Alrighty. Uh, Good to see you guys here. Sorry for that scare this morning. I got confused about my own schedule and posted your announcement with this link a little bit early saying class was at 11, and a few of you did come at 11, and I really appreciate that attentiveness, and I am sorry for frightening you. Of course, class is at 12:30. So let's get to it. Last week we talked about areas between curves, and we talked a little bit about U substitution. This week we can take a look at our syllabus and see what the main topics are going to be. So we're going to be talking about volumes, but I'll show you here where you can find the stuff just so you're able to kind of play the game from home. Turn on my screen share, and we're away. All right. So, we talked about substitution, areas, and average value last week. This week, we're going to venture deeper into chapter 6, talking about volumes through a method called the washer or disk washer method. And then there's another method called cylindrical shells. And if there's time, we'll talk a little bit about work. Work is this concept from physics. Really doesn't have anything to do with this other stuff, but it's a neat extra topic that kind of fits well here. So let's get into it. Camera's been giving me some trouble this morning, so I'll ask for your patience if it doesn't want to zoom in or zoom out. Looks like it's working now, so. This is MAC2312. We are section 004. And today is a lecture on January 12th. Today, we start on section 6.2, which addresses volumes of solids of revolution.
Hey, Professor.
Hi.
Shortly before you came into the Zoom room, there was a message from Cody Britton saying he was going to be late because his father just died, and he wanted us to let you know.
Oh shit. I'm so sorry to hear that. Yeah. I appreciate you passing that along, and yeah, of course. Okay. So we do need to talk about volumes of solids of revolution. That's what we'll get to here. Before we can get into that, I think it'd be good to talk about what a solid of revolution is. So how are we going to be thinking of these solids whose volumes we'll be finding? Volume, of course, is three-dimensional measure, right? You have a three-dimensional object, and then the space that that object occupies, usually measured in like meters cubed or some third power of a measure of length, is the concept of volume. But a solid of revolution are a special kind of solid. They come from rotating a two-dimensional region about an axis, we call it, of revolution. So the simplest example I can think of is a cylinder. Suppose I take a little rectangular region, call this A, call this B, and I have some constant function here. We'll call it f of x equals c. It's a constant function. If I take the region bounded by f of x from A to B, that's this area here, and I were to rotate it about the x-axis. So you kind of imagine that the x-axis is like a barbecue spit, and you can spin this region around that barbecue spit. The solid you would get would look like a cylinder. I'll do my best to draw it here. My art is not great. Maybe I'll draw it down here. Thinking of that being like that, and this would be like that. This would be like that. And here is my x-axis. Poking out like this. So do you all see how if you rotate something like this, you pick it up and you kind of spin it, you will get something that looks like this? Takes a little bit of work to visualize. You can kind of see this original region inside here. Here's B, here's A. And this blue rectangle that I'm drawing inside here is that original region. And when you spin that region around, when you rotate that region, it sweeps out this solid. So this is what a solid of revolution is. It's any solid that's generated by taking some two-dimensional region like that and spinning it around. Sometimes we'll rotate around the x-axis. Sometimes we'll rotate around the y-axis. Sometimes we'll rotate around other lines. But those lines, for us at least, will always be parallel to the x-axis or parallel to the y-axis. In other words, our axes of revolution will always be horizontal or vertical lines, and most often there will be one of the coordinate axes. So what we want to do is try to find some way of going from the area problem here, which you know is related to the integral of f of x, to the volume problem here. And that can be a little bit challenging, but the trick really is, at least at first here, to think about these sort of cylinders. All right. So in section 6.2, we're going to be using a particular method. The first one I'm going to call the method of disks / washers. And then the other method is called the method of slicing. And it turns out that the disk washer method is really a special case of the slicing method. The slicing method is kind of a little bit easier to understand in some ways. And the disk washer method is a little bit easier to implement. So kind of conceptually, the slicing method, I think, is the easier one to address. So I'm going to solve a slicing problem, and I'm going to solve a disk washer problem. And I'll try to help you see the connection between the two. The textbook does a good job of drawing the pictures here. So let me pop over to the textbook for just a second. Here's a picture describing the slicing method. This blue sort of bread loaf shaped blob is the solid that we want to find the volume of. The way we're going to do that is take these tiny little cross-sectional slices, and then you find a formula for the area of one of those cross-sectional slices and multiply by a tiny little thickness, and that will give you a tiny little volume. You add up all those tiny little volumes and you get the total volume. But of course, we need to add up those little volumes over a continuum, right? We can't just take some finite number of little slices. That would give you a solid like this, where the edges aren't smooth, but our solid's edges are smooth. So you need to send the number of slices to infinity. And that's how you actually get the formula, where you integrate the cross-sectional area times the little differential thickness of the slice. Don't worry about the Riemann sum thing here. There are exactly 0 problems where you will need to think of the things this way, but you will need to think of them this way. And I'm going to show you a way to sort of break this down into components that makes it a bit easier to think about. The other method we're going to use is called the method of disks or washers, and it really can be seen as a special case of the slicing method. So let me come here to a nice tractable problem, something that's not too hard to work out. Yeah, let's do this one. Let's take the square root function from 0 to 1. And rotate the region bounded by f of x equals the square root of x and the x-axis from x equals 0 to x equals 1. Rotate that region about the x-axis. Find the volume of the generated solid. So this is going to be something that we'll use the disk washer method. For all of these, we need to graph the function in question, sketch that region. Here's what the square root function looks like. This is one of our basic functions. We should know what this guy looks like. I'm going to mark this as 1. And since the square root of 1 is 1, that means the y value up there is also 1. So here's my little region. I want to rotate that region about the x-axis. It's helpful often to try and draw the solid. So I think I'm going to come off to the side here and do my best to sketch for you, at least a little version of this. This is going to look like a little bowl, right? A little sideways bowl like this. The origin is this point over here. And hopefully you guys can kind of visualize that. If I rotate this region about this axis, if I were to pick this up and spin it around, then it would generate a solid that looks like this. If I want to find the volume of that solid, one of the ways I can do that is by coming into my region and drawing a little strip. I say that this strip has thickness dx, and that the position of the strip, the x coordinate down here is just x, which means that the point where that strip hits the curve is x comma the square root of x, because I'm along the graph, f of x equals the square root of x. And the thickness, we said, is dx. If you imagine rotating just the strip, right? Forget about the rest of the region. Imagine for a second now that I want to rotate just this little dx thickness strip. That would generate a little disk. That disk has a radius and it has a little thickness here, and that thickness is the thickness of the strip. So this is the whole solid, and this is the tiny solid generated by rotating just the strip. Yeah, ALP is a step ahead of us here. So if I want to figure out the volume of this whole solid, the way I'm going to do that is by finding the volume of this little disk and then adding all of those up, because you can think of this solid as being infinitely many, infinitely thin disks like this stacked on top of each other. The way you add something up over a continuum is with an integral. So the tiny solid here has a tiny volume, which I will call dV. D for differential. It's a little differential volume. And that's going to be pi r squared, the area of this little disk, times its little thickness. And that little thickness is dx. The way we find v is by integrating dv. Now, Alt made the observation that the radius r is equal to the square root of x, and that's exactly correct, because this height is the radius, right? When this strip rotates to generate this disk, the disk that's generated has this dimension as its radius. And here, down here, y is equal to 0. Up here, y is equal to the square root of x. So the height of this strip, which is the radius of this disk, is the square root of x minus the y value here, which is 0. So dv is equal to pi times the radius squared times dx. Or just pi times x dx. And the way we recover v is by integrating dv. Right, this symbolically makes sense. X is the integral of dx, v is the integral of dv. But we need to do the integral from the smallest x value over here in my region, which is x equals 0, up to the largest x value over here in my region, which is x equals 1. So this will be the integral from x equals 0 to x equals 1 of dv. And now we can just plug things in. That's the integral from 0 to 1 of pi x dx. Now, of course, the pi pops out. I'll continue over here. This is pi times the integral from 0 to 1 of x dx. Which would then be pi times x squared over 2, evaluated from 0 to 1. And if you plug in 0 here, you get 0. So the only information comes out when we plug in 1. You get pi times 1/2, or pi over 2. And that's the volume of this whole purple solid. I have some tools to help you guys visualize what's going on here. First, I want to show you in the textbook. The textbook has some nice pictures. Before that, any technical questions like why is r equal to the square root of x, or why are we integrating this or that? I'd like to make sure we're comfy with all the details here. Does everybody see why this dimension is the radius? Why this height here corresponds to the radius of this disk? Are we all able to visualize that?
I had a question.
Yes, yes, Alexander, please.
You had said earlier that some of these might not be rotated about the x-axis, that they'd be like translated.
Yes.
Would it be easier to just translate down to the x-axis and do it that way?
No, I would say in the setting where you have some other axis of rotation, it's easiest to handle things directly rather than shifting them back to somewhere else. So I'll show you how to handle those in later examples, but for now I want to make sure we're comfortable with just the basics. It's a good question, and the answer is you could, but I don't think that's the easiest way to do things most of the time. Yeah, these are tricky. They take some time. So the catch for me, when I, as a graduate student, first had to start teaching this stuff, I remember going, oh, fuck, I hated this in Calc 2. Like, how did I do this? And the thing that finally made it easy for me to teach, the thing that made it easy for me to always remember as I needed to, was to draw in the strip. Sketch the region, draw the strip, and then imagine rotating just the strip. That's the little solid dV. Once you have a formula for the area or the volume of the little solid dV, you integrate that. So those are the steps I would break it down. Sketch the region, draw the strip, rotate just the strip. That will generate the little solid dV. Find the volume of the little solid dV, then integrate that. If you break it down into those fundamental steps, it'll work great, not just in 6.2, but also in 6.3 when we deal with the other methods. So let me show you here in the textbook, the corresponding pictures. Colors are swapped here, sorry about that. But you've got the graph of square root. They draw in this tiny little strip. And then if you rotate the whole region, you'll get this whole solid. If you rotate just the strip, you'll get just this little disk. That's why we call this method the disk washer method, because you're thinking of this big solid as being an infinite stack of very thin disks like that. Now, you can kind of picture what it would mean to have infinitely many of those little disks stacked together, right? That looks like this. And really with the integral, we are assuming infinitely many, infinitely thin disks. But this way of breaking it down, calling this strip a dx thickness rather than a delta x, and letting it, thinking of it as being infinitely thin, then integrating to add all of those up works beautifully. If you want some extra help visualizing this, come over here in the modules. Oh, sorry, this is called algebra. Where are you guys? Come over here in the modules. And look at some of these.
You're in the wrong class, Professor.
Oh, son of a bitch. Thank you. Calc 2. There we go. Right, in the modules. Specifically, so Patrick GMT is great for like helping you solve problems, but there are a few visualization links here that I think you'll like.
Okay, we
Fast forward through some of this.
here and take this small sphere. There's our curves, there's our slice. And if we start revolving
So
it,
here he's using a method
shells,
called
which would be
cylindrical
shell
shells, but it comes out
can
the
take
same
a
sort of
whole
way. You draw a
bunch of
strip
these
and
shells
revolve that, and then
to
you
form
imagine your solid as a
See
bunch
if
of
we
those
can figure
things
out how
stacked
to set
together.
this one up. So given an X value here,
I think I have one for disk washer also. Yeah, here, let's look at the disk washer one.
okay,
So again, you have a region,
we're going to rotate it
you want to
around.
rotate
the
about
X
something.
is a representative little slice. And what we're
I'll
doing
just
is
let this
we're
play for a second.
rotating that piece around the x-axis. And you notice that that's going to give us this donut shape, well, washer shape is what we call it. It's a large circle with a hole in the middle, right? And for each slice of this curve, we will get a rotated washer. And if we get a whole bunch of those, right? We get a whole bunch of those little slices and we rotate them all, then we're going to get our actual shape, or at least a good approximation of it. In the long run, we're going to get the actual shape.
All right. So I invite you guys to watch those in your own time. They are very helpful for understanding and visualizing what's going on here.
Professor?
Yes.
I just have one question.
Sure.
How would you determine whether to use cylindrical shells or the washer method?
So for now, we're just going to worry about the washers. I'll introduce the cylindrical shell method on what's today? Tuesday. I'll introduce that on Thursday, and after that, I'll give a little discussion on how do you decide which method you should use in which situation. But for the most part, it's whichever one sets up the easier integral. So kind of thinking ahead, whichever one leads to an integral that you can solve more readily is the method you should use. Sometimes one way gives you an impossible integral. And sometimes for geometry reasons, one of the methods is impossible. But we'll talk about that a little bit more on Thursday when we introduce the second method. So for now, I'd like to look at one more problem where we're using this, I'll use the darker pen, where we're using the disk washer method to find the volume of the solid generated by rotating the region bounded by, we'll use y equals x and y equals x squared from x equals 0 to x equals 1 about, we'll do the x-axis again. All right. So I want to start, all right, our steps here are sketch the region. So here my region has two different boundary curves. One of them is the line y equals x. Here's my x-axis, here's my y-axis, and here's y equals x. And the other one is y equals x squared, which in quadrant 1 looks like this. I want to take that region and rotate it around this axis. The solid that you're going to get here is a little bit weird looking. On the outside, it looks like a straight cone. But on the inside, it's kind of, I don't know how to say this, like bloopy. It's like convex on the inside. Right? It's kind of like a cone with the middle puffed up, with the inside all puffed up. And if we attack this the same way we attacked the last problem, we come in here and in our region, we draw a little strip of differential thickness. We call it a dx thickness strip. And then I imagine rotating just that strip. Something interesting happens when I rotate just this strip. There's going to be a gap between the bottom of my strip and the axis of rotation. So rather than getting the full disk like we got last time, we're going to get an annulus. We're going to get a washer shape. Okay, and my art skills here are a little bit limited. I'm sorry for that. But here's the x-axis coming into my solid. And here's the x-axis in the setting of my little disk. What you'll notice about this little disk is that he has two radii. He has like this inner radius, which I'll label as little r, and he has this outer radius, which I'll label as big R. Right, so little r is the radius of the gap, and big R is the distance from the axis of rotation all the way out to the edge of my washer. And what we want to do is come back to the picture of our region. We always draw this nice and big so that we can label the distances in here that corresponds to little r and big R. So little r is the distance from my axis of rotation to the start of my washer. So that's going to be this distance. And big R is the distance from my axis of rotation to the outer edge of my washer. So that's going to be this distance. This is by far the hardest part, right? Is setting these up and seeing what distances in the sketch of the region correspond to the distances or statistics you need on the little differential solid.
Would that be equivalent to finding the area between curves and multiplying it by the circumference, find the volume?
Similar, right? Unfortunately, we can't just like find the area between the curve and then multiply by a thickness, because each of these little volumes comes from a little unit of area times a little thickness. So it's kind of like those operations don't commute, but it's very, very similar to that. So I want to take this little height here and multiply by this little thickness. The catch is that I then need to do the right geometry to get the volume of this little solid. That's the pi r squared part, right? So it's not just the area. And because the height of this little strip changes as we move, right? Over here, that's a very, very short strip. In the middle here, it's longer. And then at the top, it's very, very short again. We have to do all of those computations before we integrate. But if we think about it, the volume of this little guy at any x value, so if here's an arbitrary value of x, I'm going to calculate the little differential solid generated by this strip at an arbitrary x value. That's what I have drawn here. And if you think about it, the volume of a big washer shape like this would be the volume of the total washer without the piece missing, minus, so that would be pi r, capital R squared dx, minus the volume of the little piece that's been punched out, which is pi times little r squared dx. And we can clean this up. This is pi times capital R squared minus little r squared times dx. So that's what my dV looks like in general for disk washer problems. And for this particular problem, big R is the distance from the x-axis all the way up here to the curve y equals x. Well, the point on the curve here is x comma x, right? Because we're along the curve y equals x. And similarly, the point down here is x comma x squared, because we're along the curve y equals x squared. So big R, the vertical distance from the x-axis all the way up to the top of this little strip is just x, right? It's this y value minus the y value down here. This y value is x, and the y value down here along the x-axis is 0. So big R is x minus 0, or just x. And little r, who can help me out with little r? What is the vertical distance from the x-axis up to the bottom end of this strip?
Y equals,
I think I heard you start to answer there, Cody, but it cut out on me. What did you say?
sorry, y equals x squared.
Yeah. So this curve is y equals x squared. So that distance is x squared minus 0, or just x squared. So remember, to find a vertical distance, we just subtract the big Y value minus the small y value. Up here, the Y value is y equals x squared. Down here, the Y value is 0. So you'd subtract big Y value minus small y value. That's x squared minus 0, or just x squared. So dV, the volume of this little washer here, is pi times big R squared, which is x squared, minus little r squared, which is x squared squared, times dx.
Are you subtracting 0?
Because the y value down here, this point is x comma 0.
Okay.
So I'm thinking of these heights as a difference of y values. So I take whatever the y value is here minus whatever the y value is down here, or whatever the y value is here minus whatever the y value is here. I'm writing it like that so that when I move this axis of rotation on you guys, from the x-axis down to the line y equals -1 or up to the line y equals 5, you're able to see how this 0 changes.
Okay.
So now I know dv. That means v will be the integral of dv. And I need to think carefully about my bounds. I need to imagine this strip moving from all the way over here to all the way over here. What are the x values from all the way over here to all the way over here? Well, this is clearly x equals 0. It's the origin. This guy is the place where x squared crosses y equals x. That's 1. So we're going to be integrating dv from 0 to 1. Sometimes you'll see me write the x equals here, and that's just to emphasize that those bounds are x values, but you don't have to write them. Now I plug in for dv, and I get integral 0 to 1 pi times x squared is x squared minus x squared squared is x to the 4. And this is the integral we need to solve. I can pop out the pi and cook up my antiderivative. Antiderivative here is not hard, it's just a power rule thing. Antiderivative for x squared, I would write x cubed over 3 minus antiderivative for x to the 4, I would write x to the 5 over 5. And again, we evaluate from 0 to 1. At 0, I get nothing because these are both 0 at 0. At 1, I'll have 1/3 minus 1/5. So this is going to be pi times 1/3 minus 1/5. And if you want to, you can have a common denominator between those two. This would be 5/15 minus 3/15 would be 2/15. So that's 2 pi over 15. I want to emphasize again that it's the picture and the setup that are important. Sketching your region nice and big with lots of space for you to get in there and label things. You see, even as big as I drew this, things got a little cramped when I wanted to label every single bit that I needed. Drawing this region nice and big is everything. Then draw in your strip. Then figure out your little differential solid. Find the volume of that differential solid by labeling the appropriate distances in your sketch. Then once you have your dv formula, once you get to this stage where you know exactly what dv is, you just integrate dv. Not too bad, right?
Is there ever going to be a time when we're not given which axis or which point to rotate about?
I'll always tell you the axis of rotation, but the axis of rotation may not always be the x-axis. So let me show you a slightly more challenging example of something along those lines. In fact, let's take this exact same problem and move our axis of rotation down. I'll hold here just for a second in case anybody still needs to write. Are there any other questions or comments on this?
Yeah, so every time we're given two functions, we're gonna use the washer method, right?
Not necessarily. There's also this other method called the cylindrical shells method. But yeah, when we're looking at the disk washer problems, the problems from section 6.2, if you have two different curves, sometimes even if you just have one curve, you'll be thinking of it as a washer rather than a disk. Basically, the disk washer method are the same thing. It's just that in the disk method, little r is 0. So if your strip reaches all the way to the axis of rotation, then you don't have an inner radius and you just have a disk. But if the little strip doesn't reach all the way to the axis of rotation, like we saw in this problem, then you'll have a little gap here. And this little gap corresponds to this little gap. And that's how you get a washer rather than a disk. Does that make sense?
Yeah.
Okay, cool. Other questions on this example before I move to a slight variation on this example? All right, let's do it. So, same as previous. But rotated about the line y equals -1. By the same as previous, I mean my boundary curves are still y equals x and y equals x squared from x equals 0 to x equals 1. But now our axis of rotation has changed. So again, I start by sketching my region. This time I'll give a little bit more vertical space. Here's my exaggerated y equals x squared from 0 to 1. And here's my y equals x from 0 to 1. And now my axis of rotation is down here. We'll call this line y equals -1. Important thing to remember, easy to forget at different times in your education, horizontal lines are always y equals a constant. Vertical lines are always x equals a constant. So the line y equals -1 is a horizontal line, a line parallel to the x-axis. I'm going to rotate around this bad boy now, but I'm still working with that same region. So I come in here, and at an arbitrary x location, I draw a little differential thickness strip. There he is. Sketch the region, sketch the axis of rotation, draw the strip. This is at an arbitrary x value. So I'm able to imagine this strip moving through this region as x runs from 0 over here to 1 over here. And the formulas we're going to come up with for dv will work for any x value between 0 and 1. That's the idea. The point up here is x comma x, and the point down here is x comma x squared, because we're on the lines y equals x and the curve y equals x squared, respectively. When I rotate just this strip, I will get oh shit, bad picture. Yeah, I don't want to draw that so that it looks like it's rotating about the x-axis. Let me redraw this down here. When I rotate just that strip about this axis, I will get something looking roughly like this. Let's see now. Can I draw this in a way that it looks reasonable 3D? Let's try. All right. So rotating just this strip about this axis gives me something looking about like this. This little thickness is a dx thickness because the strip is dx thickness. I guess I should add in this little inner wall here, make it look a little better. And again, we have two radii. Here's my axis of rotation. And I've got a little radius here, little r, and a big radius here, big R. My little radius, the inner radius, is this guy. The distance from the near end of the strip to the axis of rotation. And my big radius is this guy, the distance from the further end of the strip to the axis of rotation. And here, so dV, and this is always the case for the disk washer method, is pi times big R squared minus little r squared dx. Sometimes you'll see this is actually a dy. Just like the areas between curves problem, you can rotate these pictures all 90 degrees and set things up with respect to the variable y. We will conquer that, but I want to get us real comfy with this first. What is little r? So here, little r is what? What is the vertical distance from the near end of the strip all the way down to the axis of rotation?
X squared minus -1.
Beautiful. Yeah, that's exactly perfect. It's the y value here minus the y value here. The y value here is x squared, and then I have to subtract off the y value here, which is -1. So this is going to be x squared plus 1. And it's that plus 1 that people miss when I start to move the axis of rotation around. This distance right here, the distance from here to here, is x squared. This distance right here is 1. So x squared plus 1. You can trust the algebra. Upper minus lower will always give you the appropriate distance. So x squared minus -1 will give you your x squared plus 1. All right, what is big R?
X plus 1.
Excellent. Yeah, this would be x minus -1, which is just x plus 1. All right. So dV is pi times big R squared. That's x squared plus 1 squared. Oh, sorry, no, big R squared. Sorry. So dV is pi times big R squared, which is x plus 1 quantity squared, minus little r squared, which is x squared plus 1 quantity squared dx. I started to write them in the wrong order over here. So this is the correct order, right? This is big R squared.
Wait, so how did we get the big R?
So big R is the distance from the further end of the strip all the way to the axis of rotation.
Okay.
So I take the y value up here and I subtract the y value down here. The y value up here is x. Remember when we first drew in this curve, we labeled that point as x comma x because we're along the line y equals x. Same way we labeled the point on the parabola x comma x squared because we're along the curve y equals x squared. So the y value at this point is x. The y value at this point is -1. So when I subtract those values, x minus -1, I get x plus 1. I'm getting a little notification here that my internet connection is a little shoddy. Were you able to hear that okay? Okay, cool. So yeah, coming up with the big R and little r, definitely the two main challenges here. And the key to doing it is to draw your region and your axis of rotation big enough that you can get in there and label everything and fiddle around. Something I find myself doing often when I work these problems is drawing this shit twice. I'll sketch it once to get an idea of what's going on, and then I'll sketch it again, zoomed in on the important part so that I have room to label things. Don't be shy about doing that. So since dv is this, v will be the integral from 0 to 1, same logic as last time, far smallest x value in the region to largest x value in the region of dv, which this time is going to be pi times the integral from 0 to 1 of x plus 1 quantity squared minus x squared plus 1 quantity squared dx. And the integral here isn't challenging. I don't want to burn too much class time on it, but I feel it would also be in bad taste to leave it alone. So let me get us started on this at least. Pi integral 0 to 1. When I FOIL this out, I'll have x squared plus 2x plus 1 minus x to the 4 plus 2x squared plus 1, which is pi integral 0 to 1, x squared minus 2x squared. So I'll end up with a negative x squared. I'll write the highest order term first, though. The highest order term is negative x to the 4. There are no x cubes. I'll have an x squared minus 2x squared will give me a negative x squared. Then I have this plus 2x, he's going to hang out. And then the ones cancel. And then an antiderivative here is not hard to find. Again, it's just the power rule, so this would be negative x to the 5 over 5 minus x cubed over 3 plus 2x squared over 2, and those 2's will cancel. When you evaluate those between bounds, the lower bound you'll find again gives you 0, and you'll have pi times negative 1/5 minus 1/3 plus 1. All right, and again, if you want, you can have your common denominator, negative 1/5 minus 1/3. So that's 3/15 and 5/15. That's going to be negative 8/15 plus 1. And 1 is 15/15. 15 minus 8 is 7. So that's pi times 7 over 15. Or 7 pi over 15. So moving the axis of rotation up and down doesn't change the method as long as you learn the method correctly. Let me recap for you what it is that we've discussed here. But before I do that, questions on any of the technical steps?
So this is hurting my brain a little bit, but would the answer change at all, regardless of where you moved the rectangle? And if so, why?
So the strip here is understood to be at an arbitrary x value.
Okay.
So no, where you draw the strip is inconsequential. But basically, think of this strip generating this solid as giving you one tiny little slice of the overall solid. And what we do when we integrate, so each strip gives you a little solid with this volume. When you integrate, you're actually adding up all those little volumes. So you're saying,
okay,
when x is equal to 0, what little volume do I get? What strip do I get from all the way over here? When x is equal to 0.01, there's a little strip here. What's that? When x is equal to 0.02, there's a little strip here. What volume is that? And then the integral adds all of those up. That's what it does.
Okay, I see a little bit better now.
Okay, it can be a little bit mind-bending, it really can. And there's this multiple attack thing where you have to think about it conceptually, but you also have to be able to handle the nuts and bolts. And the more you do with the nuts and bolts, the easier the conceptual stuff will become. So I'd say take your time. If it doesn't all click right away, spend some time solving problems and reading the textbook and see if it starts to click a little bit better. Also, check out those visualization tools from Canvas. It looked like Alejandro might have wanted to say something. Alejandro, did you have a question?
No, I actually managed to know how was it.
Okay then. I'd like to look at, so let me recap. I promised a quick recap here. The method of discs and washers. We find dV as pi times big R squared minus little r squared. And then at the end here, there's either going to be a dx or a dy. I'm going to write this as a dt for now, with the understanding that dt can either be dx or dy. R is always the distance from the far end of the strip to the axis of rotation. And little r is always the distance from the near end of the strip to the axis of rotation. And dt can either be dx or dy, depending on the problem. If your axis of rotation is horizontal, then you'll use a dx. If the axis of rotation is vertical, then you'll use a dy. And the last thing I'd like to do right now is show you guys one of these where the axis of rotation is vertical. So let me see if I have a nice example.
Professor,
Yeah,
is this what you meant when you said we will use dV for a very specific thing, or no?
no, actually. So we talked about using U for a specific thing. When we talked about U sub,
Oh,
that's going to
right.
be integration by parts next week.
Okay.
So let me look at this. Let's take the two curves. So one more example here. I'm going to find the solid, find the volume of the solid, blah, blah, blah. Boundary curves, we will use not the y-axis. 2 square, x equals 2 square roots of y. X equals 0 and y equals 9. And we're rotating this about this time the y-axis. So we need to know what these curves look like. X equals 0, of course, that's a vertical line going through the origin. That's just the y-axis. Y equals 9, that's a horizontal line, right? Whose y value is always 9. This guy is a parabola opening sideways, but it's just half of it, right? So let me see, or actually it's a regular parabola opening, yeah, no, sorry, not sideways, not sideways. It's the square root function rotated sideways, so that's just your regular parabola. It's the same as y equals x squared over 4. So even I'll come off to the side and say this, x equals 2 square roots of y is the same as saying 1/4 x equals the square root of y, which is the same as saying, or sorry, 1/2 x, which is the same as saying 1/4 x squared equals y. So it's just this part of that parabola y equals 1/4 x squared, just the part with positive x values. X equals 0 is the y-axis. Just like y equals 0 is the x-axis. And then we have over here the line y equals 9. So I want to take this region, right, and revolve it around the y-axis. So here's my region. Oh, let me add something here. For the disk washer method, right, all of this is talking about the strip. The strip is always perpendicular to the axis of rotation. That's really what makes the disk washer method the disk washer method, is that you start by drawing your strip perpendicular, that's this symbol means perpendicular, to the axis of rotation.
Yeah, otherwise it just becomes a cylinder without top and bottom.
Right. And we're going to have a method for that. That's called the cylindrical shells method. So what makes the disk washer method separate from the cylindrical shells method is whether you draw your strip perpendicular to the axis of rotation or parallel. So we're using our disk washer method. My axis of rotation is this vertical line. So I need to come in here and draw my strip perpendicular to the axis of rotation.
Can I ask a quick question?
Sure, of course.
Would we do anything different if the question didn't give us x equals 0, but it already tells us that we need to rotate around the y-axis?
Yeah, but you could have part of your region over here maybe. So it's important, always check that your boundary curves really do cordon off a little region. If there isn't a clear and obvious interior part of that region from the boundary curves given, you need to look more carefully. So yeah, this x equals 0 is important because that's telling me that my region doesn't extend over here. Does that make sense?
Mm-hmm.
Okay, cool. So we sketch our region. We draw our little strip in perpendicular to the axis of rotation. Now we need to figure out what big R and little r are. The point on the curve over here, we could write it as x comma 1/4 x squared. But because my strip is like this, when that strip moves, I'm thinking of it as moving from y values to y values. So I would write this as 2 square roots of y comma y, rather than x comma 1/4 x squared. This equation tells me that the x value along that curve is 2 square roots of y, and I'm thinking of y as being my independent variable. we need to do this because the thickness of my strip is a dy thickness. Does everybody see that? Because the strip has a dy thickness, the integral is going to be a dy integral, which means I need all of my stuff to be in terms of the variable y. Now, dv is still pi times big R squared minus little r squared. This time it's a dy at the end because the thickness of my strip is a dy thickness. And here, little r is 0 because my strip extends all the way to the axis of rotation. There is no gap between the end of my strip and the axis of rotation. So little r is 0 because the distance from my near end of the strip to the axis of rotation is 0. And it doesn't depend on where that strip is drawn, right? No matter where I drew that strip in here, the ass end of the strip is right up against the axis of rotation. So little r is 0. Big R is always the distance from the far end of the strip to the axis of rotation. That's this distance. What is that?
That's going to be 2 square root y.
Beautiful. Right? I take the x value here minus the x value here. The x value here is 0. The x value here is 2 square root y. So 2 root y minus 0. That's big R. So dv is pi times 2 root y squared minus 0 squared dy. Which means that v, which we always get as the integral of dv, we just need to sort out the bounds. So I have to imagine this strip moving through this region. What are my bounds going to be? Are they going to be y values or x values?
Y equals 0 and y equals 9.
Perfect, Alexander. Yeah, all the way down here at the bottom, it's a dy integral I'm going to have to do. So I have to use y values for my bounds. All the way down here, y is equal to 0. And all the way up here, y is equal to 9. So this strip moves through this region as y goes from 0 to 9. So these bounds are y equals 0 to y equals 9, just like Alexander said. It's perfect. So that's the integral from 0 to 9 pi times 2 square root of y all squared, that's 4y, minus 0 squared is 0, and then dy. So the integral here turns out to be very easy. You can pop out the pi. You can even pop out the 4. So you'll have 4 pi times the integral from 0 to 9 of y dy, which is 4 pi times y squared over 2 evaluated from 0 to 9, which is 4 pi times 9 squared over 2. That's 81 halves. And you can cancel the 4 and the 2 if you want. So then you'd be left with 2 times 81. 2 times is 162, is that right? 162 times pi? Yeah. So setting these up is the real challenge. No doubt about that. The key to setting them up is to follow the outline that I gave on the previous page.
I have a question again.
Yes.
the y in the coordinate to square root of y and y, the y coordinate component, yeah, right there. Is that the arbitrary y that we did in the?
Yes, it is. Yep, that's exactly what it is. It's the arbitrary y value right here. So when I'm thinking about this curve as coming from the formula x equals 2 square root y, I'm thinking of y as being the independent variable. So this y is the independent variable, i.e. the arbitrary location of this strip. Yeah, that's perfect.
I had a question.
Yeah, Alexander.
What happens when the axis of rotation intersects the area that's bounded?
Good question. We are going to avoid that like the plague. It's not impossible to manage, but it's not something that you're going to encounter in any of the problems in Stewart. If we were to deal with something like that, the way to handle it would be to figure out what portions of the region are actually giving you a new part of the solid versus which portions of the region are just overlapping. So Alexander asked a great question here, and this is a fun little aside to end with. Let me imagine just for a second. Remember that rectangle from the very start of class? I had my function f of x equals c from A to B, and I said, okay, this is my region, and I'm going to revolve it like this. What if I said, for whatever reason, that my region also included some little bit of shit down here? I'd get the same solid, because as this part rotates, this thing isn't going to sweep out anything fresh. So if you had your region intersecting with the axis of rotation, it would depend on how much of that part of the region is actually contributing a new piece to the solid. If this region extended down further than the rectangle upstairs went up, then you would get something new. But if this part that extended down here did not extend further than this went up, then you would just be sweeping out the same part of that solid twice. It's a really good question. The answer really is that we're not going to encounter that in this class because it makes things considerably harder. And it doesn't really add much to the study that we're trying to do. So what I really want you guys thinking about is how to visualize a 3D solid as a stack of disks or washers, and then how you can add up all of those little volumes to get the total volume. The problem that can show up when something like what Alexander was talking about there happens is that you may end up over counting some parts of the volume. You may end up counting some sections of that volume twice. So it's the case that all the problems in the textbook are crafted so that that doesn't happen. You won't have to worry about it. But if you were out there in the wild to encounter a problem where that was the case, you would have to figure out whether the portions of the region that extend beyond the axis of rotation actually contribute something new. If they do contribute something new, then you would break that part off, solve it on its own, and then add it to what you would get from the first part of that region. But you won't have to deal with that here. So in summary, before we go, the last thing I'd like you guys to make sure you have in your notes nice and clear is this. This really is everything you need to solve all the problems that have to do with the disk washer method. So please check your notes, make sure you have everything here and this. So for the disk washer method, the volume of your little solid, the thing we call dV, always follows from this formula. If you Google, you will find other formulas, they are wrong. If you look in the textbook, you'll find some special case formulas. They don't always work, but this always works. R, big R, is always the distance from the far end of the strip to the axis of rotation. I don't care whether that's horizontal or vertical, just look at the furthest end of the strip to the axis of rotation, that's big R. Little r is always the distance from the near end of the strip to the axis of rotation, and that strip should always be drawn perpendicular to the axis. The differential dy or dx depends on whether your strip is a dx thickness, like a vertical strip has a little horizontal dx thickness, and a horizontal strip has a little vertical dy thickness. So sketch your region, draw the strip perpendicular to the axis of rotation, then start labeling big R and little r according to these rules. Then you'll want to go in and find algebraic expressions for big R and little r, assemble them into this guy, and integrate dv to get v. On Thursday, I'm going to show you guys how to do this with the cylindrical shells method, and we'll also talk about some ways that you can attack problems like this directly using neither method. That's called slicing, and it really doesn't have a lot of utility here, but it has some utility in physics, so we'll address that. And that will be our total discussion on volumes for now. At the end of the term, we're going to come back and talk about surface areas for these sort of solids. And these will play a meaningful role in exam 1. So you want to make sure that you're comfy with these methods. Your homework for this week is going to open up in about 5 minutes. So if there are not any other questions for me, I'm going to go ahead and end the meeting here. Any last minute stuff before we go?
Will there ever be an axis of rotation that's not perpendicular to the x or y axis?
Nope, we'll just stick to horizontal and vertical lines. In Calc
Okay.
3, you'll see how to do the other, right? You have to do a coordinate transform that involves some matrices if you want to do something else.
Have a great day, Professor.
You too, Up. Yeah. Any other questions or concerns before we sign out?
I do. It's about the homework for last week.
Yeah.
I requested an extension, but I don't know if it's gonna go through or if you can still.
I will
do
grant it. Yeah. So I went through yesterday and cleared out my extensions. If you requested one after I granted them yesterday, then you'll get caught in today's. So I will go ahead and grant that right after class.
Okay, thank you so much.
No problem.
Professor, this is Cody.
Hey, Cody.
I have a bit of an emergency. How can I contact you?
Canvas message is great.
Okay. Thank you.
Yeah, of course. Of course. I hope everything works out okay. Alrighty. I am going to go ahead and end the meeting here. If you do need to talk to me about anything, of course, Canvas messages are great, or you can come by an office hour. Today's office hour has already taken place, but if you need another one, just send me a message and we'll figure something out. Take care of yourselves, guys, and I will see you on Thursday.
Thank you, Professor. Have a good day.
Bye bye. Thank you.